Welcome learners. In today's lecture, we are going to continue our discussion on the behavior of electrostatic charges. We are going to first discuss the charge distribution when the shape resembles a volume charge density. We are going to understand what is the meaning of charge density and how we are going to find the effect of electric field due to these charges residing inside an arbitrary shape or a volumetric area. So the idea of today's lecture is to understand the charge distribution or various charge distribution and its charge elements. So we already talked about a single point charge, where point charge is that entity that just resembles a single dot, as you can see over here, and its characteristics is such that it has no length, it has no width, it has no radius, it has no height. So it's a simple dot. So we say that this fictitious charge is a point charge, and this is mostly utilized in the field of electromagnetic theory as a test charge. So sometimes point charge is known as a test charge. In some of the reference books, it is represented as Q0 symbol. So later on we are going to see that what happens if we have more than one charges, and in the upcoming lectures we are going to start discussion on these three kind of charge distributions. So today's discussion is on the volumetric charge distribution, but let's have a look at these three charges. So we can have charges lying along a straight line, as you can see over here. Then the charges can be on the surface of any plane sheet, and the charges can be available in arbitrary 3D shape, which we call as volume charge distribution. For all these charge distribution, we are going to use a symbol represented as rho, and if it is being analyzed or the charges are being analyzed confined in a line, we are going to represent it as rho of L. It is with the units of coulomb per meter. If it is confined in a surface, it is represented by rho of S with the unit of coulombs per meter square, and if it is inside a volume, we represent it as rho V, and its unit will be Q per meter cube. So these are the symbols that are going to represent a single value of density of charges inside any shape or any space, that can be a straight line, a flat sheet as a surface, or any arbitrary shape. So now let us understand how we are going to find the electric field due to these charge distribution whenever they are lying in volumetric space, surface, or line, starting our analysis with volume charge distribution. So charge distribution can be divided into two aspects or two types. So charge distribution can be discrete charges, which we call as or term as system of charges, and it can be continuous charges. That means it can be finite or it can be infinite. So these are the different types of charge distribution. Again, if we talk about the system of charges, we have previously seen the case of point charge or multiple charges available in space. For example, if this is charge Q1, this is charge Q2, and the point of interest is over here, so we can see the effect of this charge on this point P and the second charge on this, and then we can apply the law of superposition to find the total effect of the electric field at this point, where we know that the value of the point charge or the electric field intensity for the point charge is kq divided by r square with the unit vector a of r, k being the dielectric property of the material. So this is how we talked about the system of charges or discrete charges, but our topic of discussion is mostly now related to finite and especially infinite charges, and we are going to see how the volume is going to behave. So let us start with the first charge distribution, and that is volume charge distribution. So let us consider an arbitrary shape, and we say, so this is some amoeba like structure, and we have tremendous amount of charges inside this arbitrary shape with which we are going to find its characteristics in the form of volume charge density. So assume we have abundant of these charges in a tremendous amount lying inside this arbitrary shape. So when we look at these charges individually, we know that these are individual having their own strengths and own energies and own field lines. But if we give an overall look or we just pass by, we can say that it is making a continuous stream of charges. You can understand this analogy as such. Let us say if I have a voltage source connected to any system inside a circuit. So this is the voltage source, this is resistor on one end, we have a load resistor. So we know that this voltage is going to give rise to a current, and then this current is going to circulate and complete the loop in this circuit. So when we talk about current, we can talk about it in terms of a larger or a bigger picture or in terms of a smaller content. So if we talk about it in terms of a bigger picture, we know that current is the ratio of change of charges or charges per unit time, and these charges are in small quantity. So we can say that a system has a current flowing in the clockwise direction, and that can be a value of, let's say, 10 amps. But we can also look at this flow of current in the form of smaller elements, or we can say that these are the charges in the form of electrons are flowing one by one inside this circuit. So then we have two perspectives to analyze this flow of current. The first perspective is a bigger picture, that we combine all the charges, accumulate them and represent them as a bigger current with a value of I, symbol of I and the current as amperes. Or we can go further inside and say that these amount of charges are flowing inside this battery. So both perspectives are correct. In the same way, if we have an arbitrary shape with number of or tremendous amount of charges, we can say that all these charges can be represented by a single value. In this case, it is going to be the volume charge density rho v, and we know that all the charges will have an effect. So we can also look at a bigger picture and say the all effect can be represented by a bigger Q. Similarly, we can have the volume of this complete area to be V, and we know that this is the source which is having all these charges together. So it is acting as a source point for us because there are different kinds of positive charges inside. So now let's say if we bring a test charge in close vicinity to this volumetric division of charges, we know that these charges will have an effect on this point over here. Again, remember, this point is our test charge which we brought in the vicinity of this volume, and it is going to have its effect like an amount of electric field from this point. So the electric field is going to represent the force applied from F onto this charge Q, as we know that electric field is the ratio of the force per unit charge. So the output of the effect of the force will be represented by the electric field. Now this field can be as a bigger picture value of E, or it can be smaller dE. So what does it mean? So let us say if I look at the bigger picture, I know that I have charges stored in them and represented by the volume charge density rho v, and then all the charges can be represented by a bigger value Q. So the electric field effect at this point is represented as E. But how about if I change, or if I introduce a smaller element into the picture? The smaller element is, let us say I take a certain portion of charges, and then in this volume of Q, I can see the effect of only limited amount of charges. So in this scenario, this new area comes out to be d of V, because these are differential volumes. The charges in them is going to be d of Q, but the total amount of charges that is represented will remain the same as rho V, which is volume charge density. So now in a smaller events or in differential elements, I can create a cube and focus on limited amount of charges inside this volumetric arbitrary division rather than the bigger picture. And again, I can see the effect of this smaller cube in the form of electric field lines acting on this point P. So this is also acceptable. So this is the scenario which we have created to understand the effect of small amount of charges on point P and larger or accumulated amount of charges on P. And obviously the distance between them will be a distance vector r with its unit vector a of r. So this is what we have done. So we have understood what is a volume, what is the differential volume dV, what is the volume charge density represented as rho v. Its value remains the same whether we are taking smaller elements or we are taking larger elements. So the idea is that the analogy is similar to the current that we have seen. We can talk about the bigger picture and take the original value as current I, or we can further deep down dive into it and look at the analysis in the form of a small amount of currents or electrons moving from positive of the battery to the negative of the battery. So then we say that what is volume charge density and what it is telling us. So volume charge density or rho v basically tells us that how much electric charge is present inside a certain space, is present inside a certain, in this case, volume of space, because we are talking about volume charge distribution and its unit is coulomb per meter cube. So this is the definition of volume charge density, and it is basically telling us how many charges, for example all of these charges, how much of charges are densely packed inside a certain vicinity, in this case a volume of space with a unit of coulomb per meter cube. So now let us put this into mathematical description. Now let us say we want to write this mathematically and say we start with the effect of smaller dq or the smaller volume metric applied on this point that is giving us a small electric field d of E. So I can say that the total or the small amount of charge delta Q is represented as volume charge density and product of the small volume or the small area inside this space. So this is basically the definition of the charge. So we can say that charge equals density of volume, which is the volume per density, multiplied by the area, in this case the small volume inside this space. So this is telling us that there is a small quantity of charge in a small space. Now once we have this information, what about the value of volume charge density? So volume charge density then can be represented mathematically as volume charge density is equal to limiting delta V tends to 0, and it's a ratio of change of charges to the changes of volume. So this is the mathematical expression of the volume charge density. And what does it mean? So it means that if we have this cube and we started reducing the volume of this cube, which means the area starts to get squeezed and this cube is becoming smaller and smaller and smaller to such an extent, to how much extent as delta V is approaching to 0, we get to what we are left with only one single charge, and that is the point charge. Again remember, we don't want to go to the exact value of 0 of delta V, rather we bring it to the smallest value such that the inside the cube, when the cube starts to shrink down, we are only left with one point charge, and this expression is telling such that if the delta V value reaches to smallest value 0, we reach towards the volume charge density. So this is a tiny region inside this delta V, and which is the point charge. So similarly the electric field then associated with this small charge, so we know then the differential electric field or the small electric field that is associated with this kind of analysis will be dq divided by 4 pi epsilon naught into absolute of r square multiplied with the unit vector a of r. And this is the equation we are getting from the point charge as well, because when the cube starts to shrink, we are only left with one point charge, and this is the electric field equation of the point charge. So similarly, so we can see now this is the effect that dV is having on this point P. What about the larger effect? If I want to know what is the effect of overall of this volume over here on this point P, so again if we know the differential element, we can see the overall effect of the of volume charge on point P as well. So we can basically do what? We can integrate the elements. So we know that the effect of the total charge is going to be integral, since this is a volume, so it is going to be volume integral, and value of volume charge density multiplied with the differential volume. So what does it mean? So here the equation for the integral, since it's a volume, is going to be a triple integral followed by volume charge density, and this dV is basically telling us that this is a tiny space with volume charge density being the number of charges inside that tiny space, and triple integral basically is giving us the volume integration, which means it is covering length, width and height of any surface that is volumetric in nature. Since now we have the total or bigger picture of charge, then the total electric field effect will be what? It is going to be volume Q divided by 4 pi epsilon naught into r square with the unit vector a of r, and we further input the value of q, so it becomes volume rho v into dv divided by 4 pi epsilon naught into r absolute square into a of r. So this is the equation to find the electric field in a bigger frame of things, and if you want to find the electric field of smaller elements or differential elements, so the above equation is the one. So this is how we find the volume charge distribution inside a volumetric area. We now have the equation for the charge and the electric field for bigger things. So I can say this is the bigger picture, and this is the smaller elements or concentrated charges, smaller charges. So now once we have understood this method of volume charge distribution, let us apply it to a numerical problem and see how we can solve these problems. So before going ahead, this is what has been discussed in the main textbook, which I have previously described. So the idea is that if we have the coordinate systems with the origin at center, you have x, y and z. So this is the charge, this is the source charge surrounded inside this volumetric division, and the test charge is brought in close vicinity to this. So when it is brought in close vicinity, we can apply the Coulomb's law equation to find the values of the distance vector, where the position vector 1 from origin to dq is r prime, and the distance from origin to test charge is r. So the volume charge density is mathematically represented as such equation, which we have seen shortly, and if we keep on increasing the value to 0, it becomes a point charge. So I'll write it over here. But the total electric field depends upon the integration of the charges, and which is the value of dV into dt. And if you want to find the smaller effect of charges, then the differential electric field is going to be the ratio of the differential charges with the value of the coefficient k and the distance vector, and distance vector being from the origin, or the position vector from 0 to dq, or from origin to q, which is r and r prime dash. So again, these are the equations that we have already seen. We are just incorporating the knowledge of the smaller electric field and the bigger electric field. To summarize, if you want to find the effect of the smaller electric field, you take the differential, and you find the effect of the bigger electric field, you basically take the integral of the elements. So now let us look at an example and see how we can find the charges inside any volume or arbitrary volume. So in this example, we have been asked to evaluate the volume integral, and we need to find the total charges contained in the 2 centimeter length of electron beam shown over here. So this is the electron beam that is shown with a certain length, and you want to know how much quantity of charges are present inside this electron beam. So we need to find the bigger Q, and the value we have been given for the volume charge distribution is rho v is minus 5 into 10 raised to power minus 6 exponential power minus 10 power 5 rho z coulomb per meter square. So let us see what information do we have. So let us first know the parameters of, since this is a cylindrical system, coordinate system, so we need to know what is the value of rho phi and z, as these are the axes for the cylindrical coordinate system, mutually orthogonal to each other. So we know that the value of phi is from 0 to 0.01 meter. So I am changing the value of centimeters into meters because our main equation, the coefficient k comes out to be in meter. Then the value of phi is not given, so we'll take the universal value of azimuthal angle from 0 to 2 pi, and then the value of z is from 2 to 4, so it is in meters, 0.02 meter into z into 0.04 meter. So this is the axis data that we have been provided, and we also have been given the value of the volume charge distribution, which is the total amount of charges inside this cylinder, and we need to know what is the total charge due to the effect of smaller charges inside this cylindrical electronic beam. So in order to find the total charge of the volume, what we have to do, so we have to find the total charge of this e-beam. So we know that charge is going to integration of volume, and then we have rho v into dv. It comes out to be triple integral rho v into dv. So I have the integrals of the coordinate systems rho, phi and z, and if I incorporate the values, so let us start incorporating the values. So I can write it as, this is rho, this is phi, this is z, and value is minus 5 into 10 raised to power minus 6 e raised to power minus 10 power 5 rho of z, and that's it. And what is going to be now the value of dv? So since this is a cylindrical coordinate system and we are finding the volume, so we know that the differential elements for this scenario, so the differential elements for this scenario comes out to be, so the volumetric differential elements, so this is volumetric differential elements for the cylindrical coordinate system is going to be d of rho, then you have rho d of phi, and then you have d of z. So these are the elements that is going to replace the value of dv, which are the differential elements for the cylindrical coordinate system. So I can incorporate value of this over here, so it becomes rho d of rho, d of phi, d of z. So these are the values of the dv in this case. So once I have this, let us put the value. So the value of phi is from 0 to 0.01 for rho was 0 to 0.01, for phi is 0 to 2 pi, and z is from 0.02 to 0.04. So I'll just use the alphabets. We know the limits will remain the same. So let us see what can we do with this. So in this integral we can see that the first integral, or the easiest one to solve, is for phi. So I can start with phi, which means that rest of the elements or the double integrals can be taken out. So I'll take phi and z to be out, or rho and z to be out. Then the value will be minus 5 into 10 raised to power minus 6 e raised to power minus 10 power 5 rho of z, and then I'm going to integrate for phi from 0 to 2 pi, and this is d of phi, and the remaining differential elements rho, d rho and dz will remain. So once I integrate this with its limits from 0 to pi, it becomes 2 pi, because phi will be d phi will be changed into phi, and the limits from 0 to 2 pi gives me the result of 2 pi. So this is the answer that I am getting. Now I can further simplify this by taking this 2 pi and multiplying it with minus 5. So my equation then simplifies to, so the total charge which we are finding comes out to be minus 10 pi into 10 raised to power minus 6. So I have taken the value of the constant outside, and then I'm going to have the value of the next integral. So this gets multiplied over here. Now so the next thing I can do is, once the multiplication has been done, I can solve the integral for z. So let us solve the integral for z. This means the exponential minus z is going to be the inside of the structure. So it is going to be, so I keep rho integral outside, inside I am going to be with z e raised to power minus 10 power 5 rho of z, and this time it is with d of z, and the next value remains as rho d of rho. So this is what I am getting. Now I can further simplify it when I integrate it, so it becomes minus 10 pi into 10 raised to power minus 6. The integral for the rho remains as it is. Then if I integrate this portion, it comes out to be e raised to power minus 10 power 5 rho z divided by minus 10 power 5, and I'll be getting rho over here. The limits will be 0.02 to 0.04, and the remaining values will be rho d of rho. I can see that this row is now getting cancelled with this row, and if I can now put in the limits and proceed forward. So it is going to be minus 10 pi into 10 raised to power minus 6. I can keep row as it is and I can input the values. So this 10 raised to power 5 can be taken out, so minus 10 raised to power 5, and these negative signs can be cancelled out. So it is going to be e raised to power minus 10 power 5 rho with the value of z 0.04 minus e raised to power minus 10 power 5 with the rho 0.02. So this is what I am getting, and at the end I will have d of rho. So once I solve this equation, it comes out to be, so 10 pi, I'm going to take this 10 raised to power 5 and bring it to the numerator, so it becomes into 10 raised to power minus 11, and it comes out to be rho, and this becomes e raised to power minus 4000 rho minus e raised to power minus 2000 rho d of rho. Now I can integrate with respect to rho, so it comes out to be 10 pi into 10 raised to power minus 11, and again e raised to power minus 4000 rho divided by minus 4000 minus e raised to power minus 2000 rho divided by minus 2000, and if I put the limit for the rho, it is from 0 to 0.01. Once you incorporate the limits and solve the complete equation, the final answer comes out to be 0.0785 into 10 raised to power minus 12 coulomb, and that is the total charge that is present inside this electronic beam, which is the form of the cylindrical shape. So this is how you solve the questions related to the volume charge distribution. So now let us look at another example and see how we can go about this one. So the question says that we want to calculate the total charge within each of the indicated volumes. So the three indicated volumes are from 0.1 to x, y and z and less than 0.2. Then the volume charge density for this is 1 by x cube, y cube and z cube. For part B, it is between 0 and 0.1 for rho, and phi is from 0 to pi, and z is from 0 to 2 to 4 with volume charge density as such. And then part C is that if we have a universal condition with this volume charge density, how we are going to solve this. So let us try to solve this part by part. So the first part, we basically have been given that absolute of x, absolute of y and absolute of z are in the range of 0.1 to 0.2. Okay, so if we look at this, the value of charge immediately comes out to be 0. So this means that the solution to this, the value of charge, without going into the analysis, logically it comes out to be 0 coulomb. And how we know that it has 0 coulomb? Because this is an absolute value. So whenever we have an absolute value, the effect of a charge in the space cancels each other out. To understand this, we know that whenever we take an absolute value, it is basically telling us that the value of or the value anywhere inside the absolute is going to be positive whenever the value of x is greater than 0, and it is going to be negative whenever the value of x is less than 0. So it means that if we have a coordinate system, and if I have anything on the axis, then the same thing on the negative axis is going to cancel each other out, which we generally term as an odd function. So since it's an absolute value, it is going to have no charge because both the charges will cancel the effect of each other. In order to further understand it, let us say if I take one portion from this volume charge density and apply the odd function analysis. Let's say my function is f of f is equal to 1 by x cube. Now what is going to happen if I take the value of x as 1? So it is going to be 1 by 1 equals to 1. What is going to happen if I take the value of x to be negative 1? It is going to be negative 1. Now what is going to be the effect of total f? So total f is going to be f of x plus f of minus x. So it is going to be 1 minus 1 and it is 0. So this is why the charge is having no value. It is better even understood if I talk about the even and odd functions that we see in signals. For example, if I have this function, let us say in the time, and this is the strength of the signal x of t. Now if I want to find the negative x of t, it is just you flip the signal on the other side. So it becomes x of minus t. So you on the vertical axis, you have just flipped the signal. Now if I want to do x of minus t and take the negative of it, so what is going to happen? The x of t over here is going to get shifted and the answer will be such. So this is now the inversion of x of t. So my original signal x of t was here, and this portion is minus x of t. So you can see these both signal cancel each other out. This means hence our signal has nothing. It is 0. So this is the same thing that has happened over here, that whenever we have an absolute value, the charge comes out to be 0 because the charges in the space cancel the effect of each other. So this is the answer to the first part. We don't need to solve it. However, if I wanted to solve it in the sense that the same question is here, but now I don't have absolute values of volume charge distribution. So let us say now I have the volume charge distribution to be 1 by x cube, y cube and z cube, and the ranges or the values provided are such that the range is 0.1 less than x, y and z, which is less than 0.2. Now for this scenario we do have a solution because now we are only dealing with the positive side of the space or the positive side of the charges available. So in this case, how can we find the charge? Then we can find the charge as integral of volume rho of v dv, which comes out to be triple integral. Since this is x, y, z coordinates, so I can have x, y and z, and the value of rho v comes out to be 1 by x cube, y cube, z cube. And what is going to be dv? So dv in Cartesian coordinate system is differential element dx, dy and dz. And what are the limits of x, y and z? So for all these limits it is from 0.1 to 0.2. Now this can be solved because we have only one side of the equation, and that is positive x, positive y and positive z. So if we evaluate this integral and start one by one, so we can do this. We can make pairs out of this. So I can say x is going to be from point 1 to point 2, 1 by x cube d of x. Then I can take the second one, 1 by y cube d of y. Again the limit is from point 1 to point 2. Similarly, then I multiply with the third value, d of z divided by z cube. So this is what I am getting. So now if I integrate them individually, it will come out to be 1 by 2x square with the limits from 0.1 to 0.2. For the second one, it is going to be the same. We just replace x with y, 0.1 to 0.2. For the third one, it remains the same. We replace x, y with z, and the range limits will be 0.1 to 0.2. So now if I solve this, let's say I just solve the first one because the next two are the same, so they will get multiplied together. So it comes out to be minus 1 divided by 2, 0.2 whole square, and minus minus becomes plus 1 divided by 2, 0.1 whole square, and same goes for the other two. So then my answer comes out to be 3.75, and the same answer will be for this one and this one, so I can just cube them together. So finally my total charge comes out to be 5.27 into 10 raised to power 4 coulomb. So this is the amount of charge that is present for the provided question if we take the positive values of x, y and z and we don't consider the absolute values of this. Okay, now let's come to the second part of the problem. The second part is basically asking us that now the ranges of phi rho and phi and z are provided with the volume charge density of rho square z square sine 0.65. Find the total charge. Okay, so we need to find the total charge, so which means we need to use the volumetric equation with the rho v into dv. That comes out to be triple integral rho square z square sine 0.65, and the values of rho, phi and z now comes over here. And what is dv? So dv, as we saw previously, so dv comes out to be, this is a volume charge distribution, so it is going to be rho, d rho, d phi and dz, as we saw in the previous example. So this is the dv that we are going to use over here. So the value of q comes out to be we can start integration, but anyhow let me write all the values. So this is z, this is phi, this is rho, and this is rho square z square sine of 0.65, and the value of this is rho, d phi and d of z. So again we need to start with that integral that is easy to solve, and we can see that phi component is existing over here, so we can go with the phi component and easily solve it. So now I'll keep z and rho outside, and then I will have the phi component to be integrated. So we can do one more thing. This rho can be multiplied with this one, so it becomes rho cube as a constant. It will be outside. I'll take z square and I'm going to integrate with respect to phi what the sine 0.65 d of phi, and the remaining thing will be d rho and d of z. So once you integrate this portion, it comes out to be minus cos of 0.65 divided by 0.6, and the limits are 0 to pi, because in the question phi is from 0 to pi, not 2 pi, so that's why we have taken this limit. So once we solve this, we can move further. So this is the limits that we can apply on this. Now let us see what else we can do. The next integral that we can take can go with integral of z. So I can bring the rho out, the value of rho cube, and then I can integrate z cube d of z like such, and this value over here I can take 1 by 0.6 out, so let's take it negative 1.6, and then cos of 0.6 phi with its range 0 to pi, and the remaining elements are d phi. So this is what I am getting. So now if we solve this, the z square will become z cube by 3, so 1 by 3 can go out. If I write as rho cube, and this becomes z cube by 3 with the limits 2 to 4, because these are the limits for the z-axis. And the when I solve this cos theta, this portion with the limits, it comes out to be 2.181, and then we have d of rho at the end. So now let's solve the value of the z equation. It comes out to be um, rho cube, and this is 1 by 3, and this becomes 56, and this becomes 2.181 d of rho. Now if I integrate rho, so this will become rho 4 by 4, so it will be 1 by 4. So it is going to be rho 4 by 4 with the limits of 0 to 0.1, and this becomes, so if I multiply these two entities, this and this, so it comes out to be 40.712, and then if I solve for rho, it comes out to be, by putting the limits, 2.5 into 10 raised to power minus 5, and you multiply it with this value, so the final charge that is available comes out to be 1.018 nano coulomb, or 1 point, let me write it correctly, it comes out to be 1.018 meter coulomb. So this is the answer that I am getting. Let us confirm. Yes, 1.018 meter coulomb. So this is solution to the second part. Now what about the third part? So third part is a homework for you. You can solve this. The solution to the third part should give you the answer of 6.28 coulombs. For the third part, I'm going to write the limits for you, so you can have a go at this. Let's say for the third part, so if I say part C, the ranges for the third part is, since it's a spherical coordinate system, so remember, whenever the question says solve for the universal, so universal means it's a spherical coordinate system, and the volume charge distribution is this one. So again, for the spherical coordinate systems, the value of x's is r, theta and phi. So the r is between 0 to infinity, the theta is between 0 to pi, and the phi comes out to be 0 to 2 pi. So this is something that it is 0 to 2 pi. So you have to remember these are the universal parameters for spherical coordinate systems. So hopefully you can solve the integral now. Again, the equation remains the same. You use the value of q, which is this equation, and you find the value of dv. dv for the spherical coordinate system comes out to be what? So the voltage in this case comes out to be r square sine theta dr d theta d phi. So this is the value of dv that you are going to use to find the total charge q for the given problem. And this concludes our discussion on volume charge distribution. We solved two examples, and hopefully you will be able to solve the final part C of it.